Tá bem. Ah, já aparece aqui para mim. Deixa eu ver como é que estamos de som. Isso.
A gente pode, sei lá, tentar marcar de falar com ele, Fernanda, a gente só tira as dúvidas, você acha que
online?
Acho que sim, eu escuto sua voz também por aqui. Pessoal, podem confirmar pra gente se vocês estão escutando. Deixa eu ver se tem como estamos aqui no momento. Vamos. Tá. Opa! Maravilha. Muito eco no meu som, no do Dionísio.
Tá com eco ainda?
Ela disse que estava nos dois. Não sei se ainda tá.
Deixa eu tirar isso aqui então. Vê se ainda continua o eco. Continuou ou resolveu? Ah, então eu acho que eu vou ter que dar mute aqui, Laura. Veja se isso aqui agora para te ouvir.
Beleza, a gente marca dia 27.
Tá, agora continua a gente ainda com eco?
Ou se no e-mail você quiser falar no final, vou marcar dia 27 no horário.
Consegue escutar? Melhorou o eco?
Veio. Dia 28 eles têm reunião de conselho para passar as propostas e as estruturas.
A Fran disse que continua assim com o eco.
Pra gente ter teoricamente o máximo de tempo possível,
tá,
né?
Você me escuta, Fran? Ok.
Agora você deve me ouvir. Tá bom. Agora é só para confirmar se a gente está com muito eco ou se a gente... Ah, boa. Acho que agora deu bom. Ok. Sim. So, this is the first J Live. Hey Jay, that is going to be in English, right? Yeah. Fran, if you can confirm if there is echo right now, please. Okay. Okay, so I'm Dionisio. I'm the co-founder of J, as well as a data scientist. I'm here with Laura. Laura, if you want to introduce yourself as well. Não... Acho que a Fran não te ouviu.
Okay, I'm muted apparently.
Okay, so Laura, maybe you can introduce yourself again. I guess it should work right now.
Sure. So can you hear me now? I'm guessing
Great.
The microphone doesn't like us.
Yeah, it's this whole, IT thing, it never works. Laura, I can't hear you.
Now, can you hear me?
Yes.
Yes? Okay. So, well, third time is a charm, right? So, my name is Laura. I have a background in healthcare sciences. So, I'm not usually a tech person. So I was trained in-house, and that's one of the reasons why I like J so much, because I wouldn't be able to do half of the models I'm able to produce without J that I'm able to produce now that I have this tool in my hand. So I hope you guys enjoy it, and excuse us for our Brazilian accents, since we promised to do this live in English. So from now on, we're going to speak with you in English, because we have more followers from outside of Brazil. So if you want to leave your question, you can be comfortable putting it in English or also in Portuguese. We're going to answer you in English first, and then we'll provide subtitles in Portuguese for those who can understand our English. Okay? I guess everyone could listen me now, so it's on you, Dionisio.
Yeah, perfect. So let's switch straight to the code. So today we're solving a challenge, a Kaggle challenge called the New York City taxi time prediction. So I'm just having I know I have a really weird kind of resolution here in my screen. I'm going to give it a little bit of zoom right now. It should be fine. Let me check. Yeah. So we're basically now we're going to predict the trip duration of taxi trips in New York City using J. So this is a very interesting challenge. It's a very interesting Kaggle challenge actually, where you have all those kind of not super specific data. So you have pickup date time, you have the passenger count, how many people were in the car, the coordinates, the latitude and longitude from pickup and drop off points. Also this kind of vendor ID, which is I guess it has to do with who owns the fleet, the taxi fleet. But in the end you have to predict the trip duration. So how long it took for the trip to be completed from the pickup to the drop-off point. And I think this is a very interesting challenge to solve with J, because it kind of shows a lot of things. It shows how you can, you are free to express yourself in the modeling phase. But you don't have to worry about the cumbersome and the very, trying to be creative with feature engineering, with date time and with time aspects of the data. So you don't have to extract the months, the day, or the seconds from the data, trying to do, super specific feature engineering to have a good result. So this is the kind of challenge in Kaggle that you see notebooks with in the order of 200 to 300 variables in the end going to the supervised model, and all of them get out of pure feature engineering and external data inserted. So we're not doing that with J. We're just using J capabilities to extract meaningful data representation from the data set, so that we can have really nice results. So I will run some code. So I'm importing J right now, right here.
I would like to say just a couple of things before you
Sure.
go forward with the data. Okay. So first thing, this is our first English live, and we asked a follower of us. He was one of the first followers from abroad that we had, and the first two lives were in Portuguese, and he wasn't able to understand. So we decided to kind of honor him and ask him what he would like to see in this live. So if any of you had the same feeling that you would like to understand some of our previous lives and want to suggest another topic for the next KJ, or maybe suggest something, I don't know, if you feel like it, you can get in touch with us, and we will try to make amends with you the same way that we did with him. And the second thing, that if you want to have access to this data set, you can follow the link. It's on the description below, and you can have access to it, and also to both previous lives.
Yeah, perfect. And so we are now using J it's very straightforward. It's very simple. And just for as Laura said, we've solved lifetime value challenge and also a forecasting data set in the previous lives were very interesting also as well. And every time we use J to solve a problem, you kind of explore different ways of using good data representations. That's what J is all about. It's not an auto ML. It's not trying hundreds of models and picking the best one. It's about how do I extract the most of my data, how do I get the best data representation, and then I feed it to forward to downstream tasks such as the supervised model or similarity search or something like that. So today we start always by importing J. You can install J very simply by doing the pip install JSTQ. Okay, so you can install J and then you can generate your own auth key by doing j.get auth key and then giving your first name, last name, and your email. So this is what it takes to generate your key, and then you can just instantiate J and start working with your data collections, right? So I already have my key, so and this is our data from the challenge. So the first thing we do here is just apply a log, log1p to the trip duration, but it isn't really needed in order to solve the problem. But as the metric that we are comparing against is using a log scale of the root mean squared error, so it's the root mean of the log of the squared error. We are also applying this transformation here, but it wouldn't be needed in order to use J. So when we apply log J and then we plot the trip duration just to get a sense of how its distribution looks like. So we get this kind of narrower normal distribution. So again, it's just to make more sense of the data and see how it looks like. So it probably has a much fatter tail, and then when you apply the log, it kind of becomes more normal-like. But I guess it's not really normal. So the first thing that I want to mention here is that why would we want to have really good data representations and not only throwing things into a supervised model? It goes about a lot of things, but most important, it comes about data efficiency. So if you have very good data representation, you can use far less data in your machine learning models. So in this example, the data set itself, the original, has 1 million and about 1.5 million rows. So we are doing all the process here with just 10% of the data. So we're doing a sample, and we're getting random 10% of the rows to train the model and do all the prediction. And as we'll see, it will give us a very good result, again, because we are getting very nice data representation. So the first thing that I'd like to do here and to mention is that the trained data set that Kaggle provides, they give us one column that isn't available at the test time, which is the drop-off date time. So if you have, of course, if you know the pickup date time and you know the drop-off date time, you already know the future, right? You already know how much it did take for the taxi to go for the whole trip. But at the first time out, we're going to run the J setup for predicting the trip duration. We're going to let this variable inside the model, even if it's not available in the test set. And the reason we're doing that right now is that when we run the sample train and we drop the columns. Let me show you. So we are not doing any kind of feature engineering with the date times here. So we're just leaving the pickup date time, we're leaving the drop-off date time, we're leaving the coordinates. We are not doing geodesic distance. We're not, basically we're not doing any kind of feature engineering. We're just getting our data frame and throwing it into J. And what I want to show here is that we've built a pretty robust way of transforming dates and date timestamps into vectors, into latent representations that are meaningful and that carries a lot of information, so that you don't need to extract them manually. So if this is true, we should be able to get those two columns inside of a supervised model and still be able to kind of overfit and cheat the model and have a very, very low error on the trip duration estimation. So this is a test of, is J capable of doing kind of this subtraction, this inference of the data first, so it can exploit this feature to predict the label, and then we'll remove this as well and continue to kind of more fair running. So we've run this supervised model. J's is all based on collections, right? So we got the data frame. We call J setup. It's everything's all about J setup. So you run J setup. You might also as well run J fit. It's just an alias. It's the same parameters. It does the same thing. So you run J setup or J fit. You give a name to your collection. I'll show you why I'm calling this a collection and not just a model. It's because all those data are going to become vectors, so it's a collection of vectors. So we are passing as data our data frame, this raw data frame. We are telling J our database is a database of the type supervised, so we are providing a label for this model to work on. So we want to do quantile regression. So we actually didn't have to worry about excluding outliers and strange values from the data set. So we have a much more robust regression by doing quantile regression. I'm saying to J, estimates quantile. J will always estimates the median, the 0.5 quantile. But we are also asking J to estimate 0.1, 0.25 quantiles as well. And the label is the trip duration. So of course that's what we wanted to estimate, or the variable of interest. And we are saying that our evaluation set and our test set should have 10% of the data that we're feeding. So just to remember, we had 1.5 million rows. We got 10% of it, so we now have 145,000 rows, and 10% of that is going to be evaluation, and 10% of that is going to be test, and the rest is going to be training data. And we are also telling Jay that, please find the best learning rate possible. So learning rate equals 0 means actually auto LR finder, right? And so just for the sake of we can run some setups again later, but just for the sake of streamline the process here, I already run it, so it gives us a loss just like that. And of course we have a very, very good result. So this is this would be like the best possible. We would be the first on the leaderboard, right? But that's not fair, because we introduced a variable that's not available in the test set, which is the drop off timestamp, the date time, drop off date time. But what we really wanted to show here is that Jay is able to transform this datetime object into vectors and really do the math, do the processing with those even untransformed and not engineered datetimes in order to extract meaningful data that can then be used to predict. So we did this supervised model, we've trained the data, and we have this very, very low.
Just a technical detail.
Sure, Laura, go ahead. And we have this kind of delay between us.
Having
but,
that.
Yeah,
I guess I'm having that delay again. Yes.
Yes, but yeah, feel free.
Exactly. But we will handle it, not a problem. So, thank you. So, if you notice, he said that he would run the 0.1 and the 0.25 quantiles as well. And it's important to explain that the J automatically fills it for you. I'm hearing myself as well. So if you can continue on that, let me. Okay, I guess. Okay, now I don't hear myself. So it automatically makes the other side for you. So when you put the 0.1 and the 0.25, it will give you back the 0.1, the 0.25, and also the median, as Dionisio said, but also the 0.75 and the 0.90%. And it's the left side of the curve probability of that event to happen. Just this side note.
Yeah, that's very, very important, very interesting also, Laura. Jay always mirrors your quantiles to make sure you have both sides. So yeah. And then continuing on our training, like I said, so now we're dropping the column that shouldn't be there, which is the drop off daytime, and running J again. Now doing again the quantile estimation for the trip duration, everything equal, just that we got off the drop off daytime that shouldn't be there, which is it is pure leakage. So, and again we run, it took 400 seconds, and this is what our loss looks like. So we got an MSE of 0.18, which is again with no feature engineering and and absolutely no external data. So this is a competition very, very where people got a lot of external data into it. So and we got a very interesting result. So I guess we kind of 400, I guess, in the leaderboard, something like that. We are not really concerned with the leaderboard, but we are concerned on that we have a good solution. We have a very robust and good solution. It shouldn't be always like super squeezed out performance of hyperparameter tuning. We just want to run one J setup. Don't worry about feature engineering. Don't worry about too much of creativity in this part of the process, but you still have a very nice, a very solid solution. So that's what we got here, and with 10% of the data. And just to, I guess, to illustrate what we have done. So when we now have j.info, so collections, and I can check all of the collections that I have created so far. And this collection, which we call the New York City daytime location. So here are all our collections. So just let me get, oops. Right. So here it is. So it's a collection of vectors called New York City daytime location. It's of the type supervised. It was created at this time zone. It has 0 dependencies, and we will show you right what this means. And it has 145,000 vectors in it. So we could also check those vectors by doing j.download vectors. And we can see that we have, for each one of the rows of the data that we've sent to the supervised model, we have now a vector of the 64 dimensions that represents that vector that has been through the supervised model. And we'll show you why this is interesting. So in the past 2 slides, we've worked with self-supervised learning as a feature preprocessing to feed downstream supervised models. So the idea was that we had static features that we wanted to apply a self-supervised model to extract meaningful representations, and then use those learned representations to run a supervised model. So because of the way this data set looks like and it works, we could have applied self-supervised learning as well, but we thought it would be more interesting to apply a different approach here. So what we are doing is that we are now going to train weak learners, weak regressors, and then we'll stack them. And what does that mean? So we're training one separate supervised model for each of the feature columns of this data set alone. So we are just regressing a vector ID against the trip duration. We're doing that for pickup daytime, predicting trip duration. Every single one of those features alone, predicting the trip duration. And then we are going to extract those learned features, so those learned representations, and going to feed them as inputs together in a stacked model to perform the final supervised duration. So we are now using supervised models as pre-processing for another supervised models, which is basically the method that is called stacking, right? So we are using weak learners and then combine them with a new, we could call it a meta learner to perform the final prediction. So it's kind of simple to do that with J. We're just running a for loop and running all those setups again. So we're now having the name of the column as a parameter for the name of the collection, and also here as the data subset. So we're just sending, as I said, the feature column and the label to each one of those collections. So we're creating 1, 2, 3, 4, 5, 6, 7, yeah, 8 collections. So in total there are going to be 8 collections. And they will feed a ninth model that will, merge them all as input features to predict the trip duration. So as we see, you can't just get all your data and throw into a supervised model, or you have this freedom to express yourself and do all those kind of different modeling techniques, and you can express yourself. J isn't about that AutoML black box that you don't know what it's doing, and you don't have the option to choose and tune the parameters. So J is much more of a framework and a way of structure how you do things with machine learning than just an AutoML black box. So we're really interested in having meaningful data representations, like I said. So right now we are running those weak learners. That's why we're limiting the number of epochs to 5. So why is that? Because when we look at the training loss, this is for the first column, the vendor ID. So we are just using vendor ID to predict trip duration. So there's really nothing that much to explore and to do that. So J is just stopping at the early epochs, getting the best model using the validation data, and in the same way that we had this vector collections right here, we now have a vector collection for this regression, for the vendor ID supervised model predicting the trip duration. And we did that also with every and each other of features. So we did that with pickup data and passenger count, and those are the loss charts that we got with those trainings, right? And every one of them with the auto learning rate runner with 5 as max epochs. You can see that, of course, as a single predictor, it is weak, so we expect a much higher loss, not a lower loss. Some of them are better predictors than others, and we did that so we get those 8 collections created. So let me show you. So if we have now j.info again, we have those collections. Oops. Yeah. Oh. Yeah, so like I said, so vendor ID is one of the collections that we have created. So it has one vector for each row, and really any kind of every column that we processed has the same thing. So we got the simple train columns. So pickup date time, will be the same. Passenger count will be the same. And each and every one of them, if we do a j.vector download, we will have j dot download vectors, sorry. Will, you know, just every other, every time you run a J setup, if you're processing text with Hugging Face model, a transformer, BERT, or with fast text, or if you're processing images with any kind of you know, inception, VGG, ResNet, you always end up with a collection of vectors of J, of, you know, latent representations that you extract with J. And when you do, when you run also a supervised model, you also end up with vector representation. So, and this is really interesting, because what we are doing right now is that we are creating this this new model that is going to have a relationship with those previously created models. So what we're going to do right now is create this kind of config object. It's a dictionary that is going to help us, you know, creating these relationships in the next supervised model. So what we are saying here is the data frame that we are sending now to J has a column called vendor ID, which will relate to a preprocessed collection in J called New York City vendor ID, and the dimension that is going to be processed is 64. So we are no longer processing the vendor ID as an integer like 1, 2, or 3, like it used to be, like the vendor ID, but we are processing it going to that collection that we trained before, that we call the New York City vendor ID, and we are pulling those vectors as inputs to this new supervised model. So, and we are doing this 8 times. That's why I have this kind of helper loop function right here to create it for us. But it basically says, you know, for each column, append to the list of dictionaries the name of the parent DB, the preprocessed collection from J, the name of the column, and the embedding dimension. So when we do that, actually our data frame becomes this. Instead of the raw data that we sent in the previous setup, we are now sending an ID, an integer that is an ID that references to the ID that we have inserted in the previous J setups of the weak learners. Because they were they are mapped like 1-to-1. All those numbers are the same, because when we did a vendor ID against predicting the trip time, you know, this row was also had this index, and that's why all the columns kind of are the same right now. They have the same ID. This shouldn't be necessary this way. It could be different IDs relating to different collections. But what we can do now is that we can run again a new J setup that we call the New York City stacking, where now the data that we are sending is a data frame with those IDs, and then we use a parameter called mycelia basis, which is that list of dictionaries that we've created, pointing each one of those columns, which is the parameter ID name, to the previously created collections called the DB parent. So basically we are sending, we have 8.
Guys, I'm not sure if this is simple to understand or not. I'm sorry, Dionisio, because I'm guessing, I'm not quite sure if it's, if you guys can understand why he's doing this. So, well, first of all, it's not that we are pro or against stacking models. So he's showing you that what you can do, what you're able to build with J. So as he said back in the beginning, he was talking about feature representation and why this is important. So if you would like to stack models, you are able to do that with J as well. So why these columns all look the same? Because the index is key to J. We don't keep raw data with us. We only keep the vectors that are suitable for machine understanding and not human. So that's why we are not worried about anyone, I don't know, maybe taking the data or anything, because no human would be able to understand or to construct back the raw data from the vectors. So the way J connects your databases is through the index or through the ID that you pass to J. So when he puts all these columns with the same ID, what is he's communicating to J that instead of taking the raw data from the pickup date time, for example, you don't have a datetime column anymore. You go to the index, for example, in the first row, go to the index 67250 and pick up the vector corresponding to that index. So instead of passing to the model the raw data, it's passing a pre-processed data which is stored as a vector in a collection that was run before, that he ran before. And the way to access this vector is through its index. So that's why all the columns look the same. You don't have to run J as this. You can check our previous lives if you want to see different ways of running this. We have it linked in the description. But he's showing also a different way of running it and also a different way of assessing J features. Just one example in which this one is a good way to run. So for example, you have in your data set, you have an observation column with it that can be with free text. So you might want to extract the sentiment or the what is written in that column. So you might want to pass it through a NLP model prior to doing your model, because you want to extract that feature with a semantic meaning before running your model. So you are representing that column with a vector that has semantic meaning. So this would be an example, for example. So you can use that to have better representation of your features, and better represented features are going to give you best models. And another upsell over here, it's you can gain with that, because if you are a beginner, you probably won't know that what games you can have with stacking models or with reprocessing some columns. But if you are more experienced and you know that, and you want to add your secret sauce there and make your feature engineering and make a different way of representing your features, you are able to do that with J, and you can share it with others from your team without worrying if they're building the same representations as you, or if they're having the same best practices that you already have. So you can share them with your key and the collection name and saying, well, this feature is really good to time trip, so use it the way you want. In a more practical example, well, I have this really great feature about our products, and you can use it for demand forecasting, or you can use it to, I don't know, a price prediction, or anything that you need to build a model that you actually need the representation of your product. And you can do it in a hierarchical manner. And also you can go on vacation and leave your key with someone for them to use it without worrying that the whole project will implode. So just to give a little bit of context on why he's doing this, and it doesn't have to be that complicated. You don't have to do all stacking and everything. And we have more examples here in the channel. You can check them on the link on the description. And you can also ask questions, then we will answer you, of course.
Yeah, and also we have a Slack channel where you can also join and talk to us and have questions and try different things. We'll be sure to have the Slack channel link, the invitation link in the comments also below. But absolutely, as I said before, and we did
it's also linked down below in the description. You can access our Slack through the link.
Yeah, and what we've done in the previous lives is that we've just pre-processed it with self-supervised learning, or just throw your data in the supervisor right away, and you can have very nice results. What we are just we're showing right here is that at the end of a self-supervised learning with J, you have a collection of vectors. At the end of an NLP, a BERT processing, you have vector representations. But also at the end of a supervised training, like a quantile regression, you still have vector representations that you can use in further downstream tasks if you wish to do so. And they could be very interesting features to use in the downstream stack. So this could look a little bit complicated at first if it's the first time you're using J, or you're looking at all those dictionaries of DB parents and embedding dimensions. It could be a kind of overwhelming. We know that. So that's it's great that Laura gave more context also. But when you kind of get your hands into it, you can see it's over and over the same process, and you really you just start to want to explore more and try new things. And stacking models with J is something that it's just it's possible, and it's kind of nice doing. Maybe it's not practical for every machine learning project, but if you have this modeling desire to do some kind of stacking, you are not constrained by the abstraction level of J. You can always extract the data features and use them as you wish in other tasks. So going to the final stacked supervised model, still with only 10% of the initial data set. We will run another J setup with another collection name. We'll pass the data frame with all those IDs, and also those kind of foreign keys that we call the mycelia bases, that connect those IDs with preprocessed collections. With the same kind of task, the same label, auto learning rate finder, and the first thing that I think it's nice to see is how the loss gets tends to get smoother when you add preprocessed features, and when you add latent representations. And you can also check that our error has improved. So it made our overall model better. So using preprocessed features in J could improve your model. Now, whether it's worth your time, keeping all those models fed up with new data and doing all those supervised learnings before, it's kind of up to you. Probably not. Probably you should just have one very nice supervised model running on top of preprocessed features with self-supervised learning or pre-trained models for text and image. But if you want to squeeze every little bit of performance, you can do it as well with kind of this strategy of stacking with J. And as a kind of an additional exercise, what we have also done here is get all those preprocessed features and also merged with the original features, so that we had the standard raw data and the preprocessed vectors, so that we could maybe get a little bit more of performance. So it's the same J setup, we just called it with a different collection name. Now it's stacking plus, so it's more expensive. And again, we have our loss here, and if we can check that our results are a tiny bit, but are better than our previous models. So it's a way to keep tracking of your models and keep improving and keep trying new things, using J as a framework of how do you organize your data. What we think it's very interesting also is that you can inspect what you have done with J. So if we got like New York City stacking plus and have a J.fields, J can tell you exactly what fields have this model uses for prediction, so that you can be aware when you're going to run the inference part of the process. So we're using a vendor ID, which is all those of the data type name we named embedding are the preprocessed ones from earlier J setups. And you also have the raw data, as I said, so the original vendor ID, the pickup date time, and other features. So you can really keep track of what was used during the training of the model, so you can use it for prediction. And of course, you can download your vectors. You can always do so, and then again, all those features. So each one of those embedding features have 64 dimensions, and we combine all of them into the same number of rows with 64. So it's kind of we're condensing information after condensing information. And when we download the vectors of the New York City Stacking Plus collection, we have the same 145,000 vectors of 64 dimensions. And then, if we can plot those embeddings into an embedding space, we could use them into another model. Those representations are yours, and you are free to download them, use them as you wish. So as just a kind of exercise, we have them plotted right here with color code for the trip duration. there's more to tinker about with it. You could run this map with more iterations and things like that. But it's very interesting to compare it to the original New York City the taxi map and see that it has relations, geospatial relations, right, coded into it. So it's very interesting to note. But here we're just showing it as an exercise of plotting your embeddings so you can visualize. It's a little bit more interesting when you have like a metric classification problem, and then you have those clusters, or when you run self-supervised learning, and then you have your data in clusters because of the contrastive learning. Here we just run the supervised learning, so we really have clusters, but we can see that we have different kinds of data kind of grouped each other, which is a kind of a cluster, but it's not trivial clusters, probably clusters of trip distributions. So this is another thing that we can do. It's very interesting, and we can also just crack open our model and see everything that runs inside of it. So if we run j.describe and send our the collection name, so this is the D type, the version or the last time it was modified, the batch size it was trained on, the learning rates, how many layers the network had, how many decoder layers, basically everything you want to know about the model and its features. So it's really everything there, and this kind of completes this kind of harsh. I'm sorry if this is a little if it was too much overwhelming for stacking J models on top of each other, but maybe watching it again, maybe not at 2x, but maybe at 0.5x. You can see that it's just the same process going over and over again, and have those relationships between each other. So to build a bigger representation and a more rich regression model. So I guess for me the demo and
guys, we also encourage you to try. We encourage you to try to do it by yourself. So you have the link for the data set down below in the description, and you also have the link to our Slack community. So over there we are going to put our notebook for this live, and we also have the notebooks from previous lives there. We are building a GitHub with the notebooks as well, but we encourage you to go to the Slack community so we can share a bit of experiences as well. And we have going through the more unexperienced data scientists to the, stacking models and everything. So you can build your model and your feature representation the way you want. And another important thing is, can you imagine put a stacked model into production? And we already have an endpoint in REST API, so you can put everything into production. We are productivity first, and you've never saw in any of our medias we talking about stacking models before. We're again just trying to show you what you're able to do with J. And we are only talking with tables for now, the data tables and spreadsheets. And if you want to do combining problems, you can also combine image of your product, for example, or maybe if we had a photo of the taxi here, we could put it there, and also free text examples. So you are able to build your representation and your problem the way you want. without having to worry about what is the activation function that I'm going to use? Can I add a contrastive loss or not? Do I have to debug my PyTorch? Maybe I have a bug inside. Should I use a pre-trained model, or should I build it from scratch? And all these decisions, we already had it default for you. And we also have this, that's why the describe is so important, because you can actually see what you choose when you decided to build your representation, your feature representation. So you also have access to our documentation. You can see all the options you have there, the encoding, decoding layers, the dimensionality you can choose. You can tune each and every one of these hyperparameters that are showing the describe, and you can see how to do it in our documentation. And again, feel free to try it for yourself. And if you need any help, or if you want to get in touch, feel free to talk to us within any of our social medias. But we recommend this Slack community. We are there 24/7. We are always using J, and in different levels, so feel free to reach out to us.
Yeah, definitely. So and we look forward to talk to you guys, and let us know if you have any questions, suggestions. Feel free to open issues in our GitHub, and we'll be more than happy to help, and make sure you have machine learning, robust and quality machine learning to production as fast as possible. So that's what Jay is about. Like Laura said, we're about we're a productivity-driven framework. We're not research focused. We are productivity focused, and we want to have the best possible model, as fast as possible, but very, very robust, and having really great data representations, and reusing those data representations in across models and across problems in the company. That's what we really believe it's the key for solving enterprise AI, and solving the super high mortality rate of machine learning projects right now. So feel free to reach us. Thank you very much for your time being here, and again, thank you, and we hope to see you in the next one.
I guess we'll see you in the next Hey Jay. Yeah, sure. And well, since you're there, let us know if you're watching us from a different country, and if you'd like us to switch our language to English so we can keep doing this. And let us know if you would like to suggest a different topic for the next Hey Jay. We have some ideas, and we're probably going to make a vote as we did last time. So stay tuned in our LinkedIn and Instagram and Twitter. We usually put the poll there, and you can vote there, but you can also put on the comments what would you like to see in the next Hey Jay. Okay, see you guys.
See you guys. Thank you.